we can start, and the first speaker is Walter. And so, Walter, the stage is yours now.
Thank you, Francesco. Thank you. Hello, everyone. It's always nice to see you. You're even in this way. So today, I'm going to talk to you about the problem of multiple solutions and how it arises in the self-consistent approach, and how is this related with the limits that have been highlighted by some recent numerical results in the last years. Okay, so this is the outline of my talk. First, I will quite shortly introduce the self-consistent approach. I will remind you what are we talking about. Then I will present the numerical evidence that has been presented in the last years, signaling some breakdown of the approach. I will provide you with our analysis, our interpretation of these numerical results, and based on this interpretation, I will suggest two possible ways that we are starting to overcome these problems. So, in many-body theory, the Green's function has an important role because it's a quantity that allows you to write down, even if only formally, an expression, a series in terms of the non-interacting Green's function and the Coulomb potential. This series is just formal and most likely is divergent for all quantity of all system of interest. And the way to overcome this problem of convergence was suggested to rewrite this series and to solve this Dyson equation, in which basically the self-energy is now written in terms of G0 and V. And when solving the Dyson equation, even when you truncate the series here with a final number term, you get an infinite series of G. And this has better convergence properties of the first series. The next step to improve on this is to consider, rather than the expansion of the self-energy in terms of G0 and V, but in terms of G itself. And this is what I here denoted by SKG, which means the skeleton series. This is a better approach because it fulfills some conservation laws, and hopefully it converges faster. And has an important role in many-body perturbation theory because it's at the center of approaches such as self-consistent Hartree-Fock, the GDR approximation, and dynamical mean field theory. And in the last few years, there has been some evidence from numerical results that the approach might be flawed. So there are basically two different sets of results, one being concerning the corresponding Dyson equation for the two-particle Green's function, so the beta-Sapir equation, and we will later hear the next speaker will talk about this. Whereas I will focus on the problems that arise with the Dyson equation, namely the misleading convergence of the skeleton series. So, what can go wrong with this approach? If we calculate sigma with the G0, what can go wrong? Well, basically your series can diverge. And what you obtain when you solve the Dyson equation when the sigma diverges is an unphysical solution, which is G equal to 0. This is obviously unphysical for two reasons. First of all, because there is no doubt that G0 is physical. There is no it's clearly unphysical by itself. It's not that you can be misled by this, but also the self-energy itself is diverging. So this is already a signal that you're doing things wrong. When it comes to the skeleton series, things can get more subtle. And here is a brief account of the work by Kozik collaborators back from 2015. So they focused on the Hubble atom, for which they can calculate G and the self-energy analytically, they had access to very high order terms of the skeleton series, and they used it, and they found this anomalous behavior. So basically, for the weakly coupling regime here, for U equal to 1, this is the convergence of the skeleton series evaluated at the exact G, and you see that it converges correctly to the red line, which is the exact solution. Here as well, but here, you see that it converges not to the red line, but to the yellow line, which is an unphysical solution, which is not the correct self-energy. So let me state it in this way. The skeleton series evaluated at the correct the correct Green's functions for the weak interacting regime converges to the correct self-energy. But for the strong interacting regime, converges to an unphysical solution, an unphysical function, an unphysical self-energy, sorry. So this is basically the main problem that they found. They also calculated other things, but I think that the core of the problem is this one. And this is a problem because for real systems, we don't know in which regime we are, in the weakly where the series converges, or to the correct answer, or in the strong coupling regime where the series converges to a wrong answer. Some progresses have been made in understanding in which regime we are, but then it remains a bigger question. What do we do if we know that we are in the wrong regime? This remains an open question. So in that paper, they conducted the analysis and concluded actually that the Latinger-Wald functional has several branches. To explain a bit their analysis, I have to make a step back and explain you what is the Latinger-Wald function. So we started from a series that is in terms of V and G. And this can be derived by manipulating and rearranging the perturbative expansion of G. But this is a divergent series. So from a formal point of view, this is not very satisfying. There is a non-perturbative derivation of the approach, which is based on the Latinger-Wald functional, from which the self-energy in the skeleton series can be derived as a function with functional differentiation. I'm not going into the details of this, but the point is that the existence of the Latinger-Wald functional relies on the correspondence, on the one-to-one correspondence between the interacting and the non-interacting Green's functions. So the result of having a skeleton series that converges to an unphysical result, according to Kozik and collaborators, was interpreted as a failure of have a well-defined Latinger-Wald functional, which is based on the fact that the map between interacting and non-interacting Green's function is not one-to-one. So that was their interpretation. And back in 2017, we suggested another interpretation of their numerical results. We started from the fact that we kind of believe that there is a one-to-one correspondence between G and G0. And we provided an argument in the article for real systems, but we analyzed exactly the Abba datum, and for that we managed to prove it. What does it mean, this? This implies that there exists a self-energy functional which can be used in the self-energy Dyson equation, and the solution is unique among the Green's functions. However, the Green's functions are not all two-point functions. And this is a subtlety that in that paper was not well emphasized. The consequence of this is that even though the self-energy functional exists, this equation here can have other spurious solutions outside this range. So basically, our interpretation of the numerical results of this misleading convergence was that the skeleton series does not converge to a good self-energy functional everywhere in the domain. So we interpreted that as a failure of the skeleton series, not the self-consistent approach by itself. And now I want to stress a bit this. Is it really a failure of the skeleton series? So what they showed here was, again, calculating the skeleton series at the exact G that they knew from other sources. And they realized, basically, they found out that when when the G is in a weak correlated state, basically the convergence works as you expected, that it gives you the correct self-energy, but otherwise it doesn't. From this, it is tacitly assumed that you cannot use the skeleton series to calculate G in the strong coupling regime. But is this always true? So when you do this again, when you deal only with the bare quantity, when you deal with G0, what do? You start with the system, you have your G0, you calculate the self-energy, you truncate this series here, and once you have your self-energy, you plug it into this explicit solution of the Dyson equation. And this gives you your G. Whereas when you have a self-consistent G, when you have a skeleton series, when you have a series which is based on G itself, you don't go through calculating the self-energy by itself, but you solve the self-consistent Dyson equation. And this gives you the G. What I'm trying to say is that you never use the series if not in the Dyson equation itself. So the series is a part of a bigger procedure. And my claim is that even if you calculate the series at the exact G and you see that it doesn't converge to the correct self-energy, this is not necessarily, it is not necessarily true that you cannot use that that skeleton series in that regime. This is a claim, but I'm going to show you an explicit counterexample. So let's go back to the Abbott atom that they studied. Let's look at this series here. This is not the skeleton series, but has the same properties of misleading convergency of the skeleton series. So you can see here, this series that I called skeleton prime here converges to the physical solution only on a limited range of the parameters of the theory. Otherwise, it converges to an unphysical solution. So this is suffers the same pathology that the skeleton series has. And yet, when you use it to calculate G as in the self-consistent Dyson equation, you do go to the correct G. Here, I'm plotting one single point because the convergence is not easy. But here you see, I am in this in this regime in which the skeleton series by itself, calculated at the exact G, will converge to an unphysical result. But when used in the procedure, in the self-consistent Dyson equation, it goes to the physical one. So this is the first way out of the problem. The skeleton series may still work in all regimes. In other words, what they showed is not a definite proof that the skeleton series doesn't work for what it was designed to do, namely getting G out of the self-consistent Dyson equation. From our example, what we learned was that the stronger the regime, the slower the convergence of the series. And this may be a practical problem. And also, from our example, what we got was a multiplication of multiple solutions, or spurious solutions. The higher the order, the more the spurious solutions. So if this is true also for the skeleton series, this becomes very complicated, because for very strong interacting regime, you would need very high very high order terms. But if spurious solutions multiply with higher terms, it might become very hard to understand which one is the correct solution. Okay, so I should mention that there has been a paper doing exactly what I was suggesting here with the skeleton series. And this is just a preprint, but I want to mention it. I don't know if any of the author is in the audience. But basically, what they show is that they used the skeleton series in two regimes, again for the Abba datum, in weakly coupling and a strongly coupling regime. In the weakly coupling, they calculated G, so not exactly what Kozik did, but exactly what I was saying, calculating G in the self-consistent equation, and they got the correct answer. Here in the strongly coupled regime, the series seems to converge to a wrong answer. So from my perspective, this is still not a definite proof that the approach doesn't work, because as I told you, there are many spurious equations. There might be spurious solutions of the equation. So there might be another way to iterate this equation and find another solution and find the correct one. Just let me show you. You see here, you might be misled by any of these solutions here. If you track the wrong solution, you might end up here rather than here, but you might miss it completely. Okay, so to recap a bit, the first solution is maybe what we are looking at is not really a problem of the approach. Even if the skeleton series has this anomalous behavior, it doesn't mean necessarily that it can be used in the self-consistent approach. On the other hand, this may entail practical problems, very slow convergence, spurious solutions. We don't know how to identify G's, the physical G's. So how do we overcome these practical solutions? Well, let's look for a better series. Easier to say than to do it. But let's go back for a moment to the Abba datum once more. This is the skeleton series, our skeleton prime series, not the skeleton, but the series that behaved like the skeleton series.
Maybe no, it's just because you have the same figure as before. Rex was asking what is omega n, just for him to understand the figure.
This is yes, this is finite temperature Green's functions. So these are the Matsubara frequencies. Okay. 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 So back to this. So in our analysis of the Abba datum, we were using this skeleton prime series, which had the same misleading convergence of the skeleton series. But we also had another series, the strong interacting series, that was previously introduced by Stan and collaborators in 2015. The other series has is basically a complementary series to our skeleton prime series, because it converges to the correct equation, to the correct self-energy, whereas in the strong coupling regime, where the skeleton prime does not converge. And when we use the same series in the self-consistent Dyson equation, we get, just like for the skeleton prime, we get the right answer, but the stronger the interaction, the faster is the convergence of the series. Okay, so this is how I would picture real systems will work. So we said that we believe that there exists a good self-energy functional. And probably what we are looking at is just a convergence of the skeleton series only on part of the domain. What we wish to find is a complementary series that is good for the other opposite of the domain when the interaction is very strong, and perhaps bridge between the two eventually. How do you do this? Well, you need a non-perturbative formulation of the problem. The point is that in the, for our skeleton prime series, we were able to work out the complementary series because for the Hubbard atom, we knew all the solutions analytically. And in the paper, this is what we used. But we also know, we also have a different procedure to derive both the skeleton prime and the sin series without knowing the actual solutions. And it is possible to to apply this approach, to transfer this approach from the Hubbard atom to real systems. And we're working on it, but it's very complicated, as Lucia can testify. So to conclude, the self-consistent approach, we have seen some, what I would say, counterintuitive results, which for me are not definite proofs of its failure. The analysis of these results requires very much care in talking about functionals, in distinguishing between non-perturbative definition of a function and its perturbative counterpart, about domains, because only if the correct set of interacting Green's functions and the correct set of non-interacting Green's functions is defined, then you can see whether the map is one-to-one. And the fact that these domains are just subsets of the all two-point functions leads to a problem of multiple solutions. And this has not, this is very important, it has been neglected. So basically, my take-home message is that we have to make an effort to understand the disease to find the right cure. And that's it. Thank you very much.
Okay.
Thank you lots. So I propose to have the question session now for Walter's talk. Let's try by unmuting yourself and trying to speak. If it becomes too complicated, just raise hands if we see that there are too many people talking at the same time, and I will give the floor to you.
May I ask a question?
Go ahead.
Sure.
Thank you very much, Walter, for recap all the aspects on the self-consistent side of the problem. I wanted to understand better the plot where you really have all solutions, so to say, plotted somehow. Where you say that you have many of them. So
here,
how do I understand better this plot? So because so can you explain me the meaning of all the just
yes. Sure. So here I've solved the self-consistent Dyson equation with the skeleton series,
yes,
with my toy skeleton series, not the real skeleton series, but my skeleton prime series, up to a certain order. So the order is here.
I see. Yeah.
Okay. So for each order, you get a certain number of solutions. So for instance, at 0 order, you get one solution. At 1 order, I don't remember exactly how many are they, but a few orders here, you start having, for instance, 1, 2, and 3 solutions. At the 20th orders, you have 1, 2, 3, 4, 5, 6, 7, 8, all these solutions here. And you see, if you have a good criterion to keep track of the good solutions, you end up with the converging to the correct function, which is this green light here, green line here.
Okay.
Otherwise, you might end up in this mess here, and you will never. You can either not reach convergence or not, or be converged to a wrong result.
And if I understand correct, your main message is that you think that if you consider the mathematical space of all green function, so all 2 points, so let's say one particle green function, in principle you will have to deal with all these multiple solutions, which what we have seen when they cross one with the other create the bifurcation and the vertex divergences. But you say, if I have a good criterion to stay on track, so on the physical one, which is a restriction of the possible G that you allow, then your functional should be properly defined for all values of U. Is this, can you summarize like this?
Yes, yes. Basically, just to make it a bit, say it a bit differently. So you have a set of physical Green's functions. I define from the onset a set of what are the physical Green's functions. And then from the theorems, I know that I will have only one solution in that set. The problem is to recognize that set.
Yes.
In my case, it was easy, because the spurious and physical Green's functions were very much different. But for the real system, we don't even know how close can we get. I mean, how close can a spurious solution get to the real one?
Actually, that was, in some sense, what we seen what we briefly discussed in 2017. So it's related to this, in the sense that there were many crossing of physical and physical solution that we found together with Ulle Gunnarsson. And the first crossing were clearly with some green function. The unphysical one was really so unphysical that you, so to say, you were just thrown away, because the double occupation was increasing with you. I mean, so you understand. But the farther you go in U, then you have other crossing with the green function that, seems to be almost perfect. But I mean, so in order to find the bug in them, you have to look very, very closely, so to say. And the farther you go with you, the worse this is. But I think it is consistent with what you are showing here. That.
Yes. Okay. No. What you just said is perfectly consistent with what I said. The problem is that. The problem is that we don't know how to distinguish the physical one from the unphysical one.
One would need a restriction of the functional space, and a restriction that work for the first crossings according to our calculation do not work for the higher order crossing. So I mean the violation of physicality at the beginning is evident. And then it becoming more and more subtle. The problem is also that we know that in the MFT, at least, at U equal UC2, so if you solve the Haber model in the MFT, or the Haber atom but going towards U infinity, then you have even an accumulation points of these divergences. And therefore, I mean, either you have a really general criterion which works for all of them together, or you cannot try to fix each crossing at time. That was my message.
Yes, thank you for this, because I'm only playing with these toy functionals here, so I'm not aware in which the wrong solutions are obviously wrong.
Yes, sometimes there was a violation of particle Hall symmetry, and that was easy to find. Sometimes you have only slightly violation of some general high frequency dependence or low frequency dependence that you only can dig out if you have a very careful analysis. And this was becoming worse and worse. The problem was that in the phase diagram, the divergence line were accumulating. by going, so they will become denser. So you have many crossing, they become somehow more, they occur more often. But of course, if one could get the criterion, one would stay on track. That I agree.
Yeah, my main message was that the real solution is hidden there.
Yeah, absolutely.
Okay, there is another question in the chat, but before that, since you are in this graph, can I just ask you here? I want to know, given an order, let's suppose that we just focus on a certain order. You have many solutions.
Right.
Is this the situation that you obtain with all regimes, or just in a certain regimes? For example, you increase your strength and you obtain more solution. I mean,
what I'm saying is true for this toy self-energy function. So I don't know how it works for the skeleton series in general, but for my toy skeleton series, the number of solutions is independent of the strength of the interaction. It only depends on the order of the interaction, of the order of the truncation of the series.
Okay. So.
Yeah.
Okay, so maybe you can read yourself the question in the chat.
Yes, are the higher function derivatives of the Latin algebra function somehow different at the physical and non-physical solutions?
If I may add to this, I was just wondering, that sometimes if you have unphysical solutions, it shows in unstable susceptibilities being negative or masses being negative. So I was just wondering whether you could distinguish somehow from.
It is a very interesting point. I have never thought about this, but it might be also related with my picture where basically the underlying functional is not perfectly analytical, so it has some kinks and stuff, so it fits well, but I don't know, it's a very interesting point. Yes.
Okay, thank you.
It might be a good way actually to solve this. Yeah.
If I may, so from our combined analysis, we know that when the solution crosses, of course, the solution is still physical. So there are crossing between non-physical solution and physical one. So at the crossing point where the problem happens, the irreducible vertex diverges. So we prove the so to say the equivalence between the existence of multi-equal solution and crossing with the physical one, and the divergence of the irreducible vertex function in the Bethe-Salpeter equation. So your irreducible vertex function diverges at the crossing point. So when a physical solution crosses an unphysical one, and you can understand this intuitively if you think that the sigma over the G is gamma, so the irreducible vertex. If this is diverging, this creates a sort of non-univocity between the green function, the physical, and the G01, if you want, and therefore this is something that you see in the formula in the irreducible vertex, in the core of your Bethe-Salpeter function. On the other end, I agree with Walter that we don't know about the physical green function of the physical susceptibility. What happens if you follow the unphysical solution? We don't know that.
I'm reading Rex's question here. If with t going to 0, or things get better or worse?
Yes. Shall I just expand on that a little bit?
Yes, please.
You've chosen to use the Matsubara formalism from the start.
Yes.
So I was wondering, at a given order of calculation and with all the other parameters kept constant, if you let the temperature go to 0, does the problem get better or worse?
I don't know. I haven't tried.
I asked because this is a pure speculation, but I was wondering whether the difference between the wrong solutions and the right solution might be the behavior in between the Matsubara frequencies, so that it might be quite easy to actually distinguish.
Why do you suspect this?
Well, I haven't done the analysis, but I'm sure we're all familiar with very simple-minded analysis of a set of equations with a given number of unknowns, and just counting the unknowns, counting the equations or the constraints. Somehow, I just suspect that if you're working at a fixed finite temperature, then the number of the spacing between the Matsubara frequencies might affect that balance between number of unknowns and number of constraints.
Alessandro, do you have an answer?
Well, only from I don't know. I think would be for sure worth it that you change. If you can change the frequency space, it would be worth. I'm afraid that the problem is not going to disappear, because since we demonstrate analytically the equivalence between what Walter and the group of Lucia Reining and Kotzik found, and the vertex divergence, and this is a one-to-one correspondence, we know that the vertex divergence are not going to disappear by going toward u equals 0, toward t equals 0, but they have a finite intercept on the t equals 0 axis. So they simply remain, or even though if their structure in frequency becoming denser and denser. I think there was even a calculation made by Sergio in which he was even able to find the divergences in a very simple model, the binary mixture model, on the real frequency axis directly. Therefore, since we have the correspondence between our problem and Walter's or Lucia Reining group problem, I think so. I suspect that if you change the omega n spacing, although it will be worth to do so, you will not. It's not going to improve much. Even going worse in the atomic limit case. I have also a somewhat physical explanation of that, but this is better that maybe I postpone to my talk because I have the slide there.
But can I add something to this? May I add something? Maybe Rex is right in the sense that one could imagine to make an ansatz of the Green's function with a reduced number of parameters at higher temperature. And of course, if you have an ansatz that constrains the Green's function to have the usual pole structure to be well behaved, and you plug this in your equation, you might get a unique solution if you have the correct ratio between, equations and number of parameters. So that sounds like something that at higher temperature one might want to try.
Just to understand better the argument. So at low temperature would be, you would expect that you will need more parameters to.
Yes, yes, you would have to fix more parameters, yeah.
That's definitely worth to try in such a way. What I can say from my side is that by looking at the structure of vector divergences, for instance, exactly in the Hubbard atom, you see that at t equals to 0, you get even half of your spectra, which is negative. So you have crossed really many, so to say, many divergency line. And this is related to the suppression of charge fluctuation that you have there, which is maximal at t equal to 0. That's why I'm not sure that so I think that higher temperature should be better than worse, because it's more perturbative in some sense.
Higher temperatures would be better.
Yeah.
Exactly, yeah.
Okay, that's also your. No, I sorry. Then I mix up with the. I thought I misinterpreted what Rex was saying. Then I thought it was hoping that T+0 was better. No, I fully agree with you. High temperature is better. I think there is. I see some Friedrich.
Yes.
Friedrich has a question.
Hello. Yes. So these solutions to these systems, whether physical or unphysical, you obtain them in an iterative scheme, right, with updates?
Which one? Yes, yes.
Yes, so you have one solution and then you go in steps to the next one and so on. So that's a fixed point scheme, and that has also a Jacobian, which determines the stability and to which solution you can converge. Do you know whether this problem has been also considered in terms of this Jacobian?
I don't remember. You mean for the skeleton series, for the real series?
Yeah, so you form a fixed point function which is supposed to vanish at the solution you're looking for, and then this fixed point function you can even determine with some approximate methods. You can determine a Jacobian, and that eigenvalue structure of this Jacobian determines the attractive and the repulsive solutions. Because this is also in DMFT, when you have the coexistence region, then there's also present an unphysical solution, but it is not. But it is repulsive. So fortunately, we don't converge there. But the Jacobian exists. You can calculate it, and it would be interesting to know about the Jacobian of these functions here, because maybe there are also ways to mess around with the Jacobian, and then you can actually converge to different solutions.
Yeah. Do you know why the Jacob? I mean, why is repulsive?
Well, that just turns out to be. So there are two stable solutions in the Mott regime. That's the metallic and the insulating one. And they both have eigenvalues which are smaller than unity. And the unphysical one has one which is larger than unity. I can send you a very nice paper by Hugo Strand about this.
Yeah, actually, playing around with this, with the toy model that and the toy and this toy self-energy function. I mean, I also tried different algorithms and for root finding algorithms, and I found a certain class of root finding algorithms that always gave the correct answer, that never end up in an unphysical answer, but I could not explain this.
Ah, yes, and I would assume that this is precisely because of this, because these methods are much smarter and they know about the eigenvalue structure. And then you can sometimes, you can even manipulate it. You can see whether you can add something to like a row and a column to this Jacobian, which will give an additional constraint, and then perhaps you can see that it converges to the unphysical solution.
This is actually crucial because when I mentioned what is when I mentioned this, I suggested exactly this, that maybe they are trying sort of converging to the wrong answer. Maybe playing with the algorithm will help you, because what I observed is that also keeping the same algorithm in all regimes may sometimes switch between right and wrong solution. And I did find a class of good algorithms, but I could not explain why they were good, why they were always giving me the correct answer.
Yeah, okay. I send you two references,
yes.
And maybe they can help with this question.
Thank you very much.
If I may just add, actually, I think Lucia agrees with me. We have analyzed this in the...
Yes, in your earlier paper on the...
We did with Giovanni, and then we did with Arian. And in fact, we analyze in terms of a fixed point that can be attractive or repulsive. And you have it depends on the algorithm that you use. If you go to a physical solution or to a physical solution, and it might be also due to the U, in the sense that the same algorithm may bring you to the physical solution if you increase U. So this we have done in the very simple model. But I guess, Walter, you can do something very similar in your about the atom.
Yes, yes, sure. Yeah, no, formally they're equivalent. So yes.
So yeah, so this you can.
But understanding how to make this work for the real, well, for the skeleton series is the challenge, is the real question. Understanding how it could work in our, and why, if this could work for the real series. Yes. Yes,
that's right. But for example, for this simple model, then we saw that what we were getting from this simple model, so for example, which kind of iterative scheme gives you the good solution and which one the bad solution. Then we applied also to a simple case, what was the optical spectra of lithium hydride, so a realistic system. And we also we found that the iterative scheme that were working for the 1 point were working also in that case.
For a real system.
Yeah. With a different problem, but again, with a Dyson equation to solve. Right. So I think it's important to also learn from these simple models, yes, and then to extend. Okay, so just a comment.
Good.
Anything else? Again from Friedrich.
Sorry, Alessandro?
I see Friedrich has again a question, or is the old one?
No, I just didn't lower my hand. I'm very sorry.
Sorry. My fault.
Okay, so I stepped down the stage, right? I thank you again, everyone.
If there are no other questions, maybe we can have we have planned a 10 minutes pause.